Okay, so we'll begin now the last talk of the day and we'll talk about real-time energy data analysis with Storm. It will be a two-voice talk. In fact, it's a common work between Octo Technology and EDF Research and Department. We are both part of research and EDF Research and Development Division because Rémi Cessy from Octo couldn't be here today. So I am Marie-Luce Picard and Charles Bernard, who is with me, who helps us in working in this project. We will present you this work. So the agenda for the talk is the following. First, I will present briefly the context of this work. Then we will focus on the objectives of using CEP for real-time analytics in our context. Then Charles will detail the architecture that we have chosen and the results obtained, and then we will conclude. So we're part of EDF Group. EDF stands for Électricité de France. It's a French utility company. It's a big company. It's the historical utility in France. It covers all utility electricity businesses from generation, transportation, network distribution, sales, and trading. And it's a worldwide company having nearly 40 million of customers. Most of them in France and in Europe. In this company, there is an important research division because we are more than 2,000 people working for research, mainly in France. We have also a few centers in Europe and a few people working here in Palo Alto. 30% of the activity is a corporate activity, and we're working on different subjects. And for example, in IT and big data, this is part of this corporate activity. And the work that has been achieved is part of a project on big data covering storage, analysis, and business issues for big data. Just a few words on Octo. I'm not from Octo, but I can just say that Octo is an IT consulting company of more than 200 employees, and they work on big data and agile development, etc. You can find more information in their website. So why EDF? Why an electricity company is coming to a Hadoop Summit and presenting work on big data and on Storm? Well, in fact, you know probably that smart grid are developing everywhere in the world, motivated by economical constraint or environmental constraint, and that implies the deployment of smart meters, and these meters are producing a huge amount of data. This morning we have a keynote from AT&T speaking of the important increase of data with the smartphones. In fact, with the smart meters, we can have more or less the same phenomenon, even if the volumes are not so huge for our utilities. You can see, for example, that at the moment we have two information a year dealing with the consumption of our customers, 2 indexes. And with the smart meters, tomorrow we will have 1 information a day. So that is 20,000% more. And if we have a measurement every half hour, it is even more. It is really a huge disruption in our company and in our business. So the smart grids and the smart meters will lead to the creation and the use of really a big amount of data that we have to store and to manage. So it changes a lot the way the business is coming and is done in our company. But the whole sector is evolving, and there are a lot of third parties implied also in this smart grid and smart data. You're probably aware of the green button here in the United States, and in Europe and in France there are also other similar activities and similar things that are coming. So there are a lot of issues dealing with data, big data, linked to smart meters. Today, we will just focus on using a complex event processing system for real-time analytics. So we made a POC on Storm a couple of months ago, and our objectives was to evaluate Storm capabilities for various analytical needs. The POC was made on data coming from meters on time series. We wanted to run simple analytics like building KPIs, or complex one like running machine learning algorithm, for example, to forecast consumption. We wanted to see if we could merge data in motion, streaming data with data at rest, data in databases, and with some performance constraints, even if they are not so extreme than in other type of businesses. In fact, in the project, we have skills on CEP. CEP tools, we are using CEP tools for several years in the project. We are used to more industrial tools, we would say, commercial ones. For example, Streambase from TIBCO now, or IBM tool that we have also tested. So we wanted also to have a deeper understanding on how Storm was working, on the concepts that were underlying Storm, and to compare with other CEP tools. This slide shows you the functional objective. The functional picture of our POC. So at the left, you can see the data that we were using. So we have a smart metering data, which is a streaming data. We also need to have weather forecast. We could have interest on having dynamic pricing also to make an evaluation, a forecast of the money that we will earn, and we have customer data that is stored in a database. Then we we build a Storm topology, and as outputs, we want to make simple aggregations. For example, compute an aggregated curve at national level or regional level, or by tariff, by different customer characteristics. We want to make analytics, for example, to score some of our customers, and finally to make forecasts. You see that in the picture we have mentioned R. In fact, in our company, in the research division, our data scientists, they love to use R, and they don't want to change. And the idea was to see if we could integrate their scripts, their models into Storm without having to rewrite lots of things. I will just make two quick zooms before talking about the architecture. First, a zoom on data, and then on the analytics. The data. I've talked about smart metering data. In France, EDF has 35 million of customers. So we have 34 million of meters, but these meters are not deployed yet, so we don't have the data. We don't have all this data. So we have to generate the data. So we have built a generator that is able to generate very quickly all these curves with statistical characteristics. The idea is to be able to see a very volatile individual curves, and at the same time, we want that the simulated aggregate curve is similar to the real aggregate. So there is a reference in the slides at the end, and you can find information about this simulator. The second zoom is on analytics, on the analytics that we want to perform. First, we wanted to build some scores based on the load curves of our customers, and before applying this course, we're using a Sachs transformation. Sachs is a famous, is a very common algorithm used on time series. It allows to transform a time series onto letters, and then you apply some other algorithm on this representation, and it's easiest, and the volume is reduced also. So you can also see a reference here, and it's a Java code that we have integrated into the topology. And finally, for forecast the demand, the consumption of our customers, we are using GAM models. GAM stands for Generalized Additive Models. Once again, it's a very common algorithm. We use a package written by Simon Wood, who is an English developer. And we have applied lots of time and in the various contexts for a more or less aggregated curve on electricity demand forecast. And you also have a reference. The idea here is to have our model built on historical data, and this model can be updated online. So it's online machine learning using the latest data. Then Charles will talk about the architecture.
Hello. So when we started this project, we didn't know much about Storm. We are newbies, actually. We haven't done anything with Storm yet. So at first, when you look at Storm, it can seem scary because you have many concepts to understand. But it's easy to be up and running, actually, because the documentation out there is very rich, and the community is very helpful. So at first, we started with a Storm-dedicated cluster. But when HGP 2.1 got released, it packaged Storm within the stack. So we moved all our topologies onto the new cluster, and it ran straight away. It's composed of 11 nodes, 1 for the Nimbus and 10 for the supervisor. It's kind of easy to install with Ambari 1.5. Actually, you just need to click the next button. It's easy as that, really. It took 2% to develop this project with development, architecture, and statistic skills. It took about 30 days to implement. So this is the use case I'm going to focus on today, which is the most interesting for us, technically speaking, because we use R within a Storm topology, which is not really common, as you know, maybe. So as Marius said, since all the smart meters are not deployed yet, we had to develop a piece of software called Turbo Cobogen, which simulates the smart meters, the 35 million of smart meters EDF is going to deploy across France. So it emits tuple as fast as it can. So this is a tuple, so it's only a client ID, a contract ID, a timestamp, and 48 measurements in kilowatts. Sorry. It's 1 meter readings every 30 minutes. So I go back. This was a typical load curve, actually, electricity consumption. So we use Redis as some kind of buffer. So Turbo Cobogen emits data, puts that in Redis, which is a key value database, which is really fast to read from. We use Redis as we didn't want this to be a bottleneck there. So next, you have a spot that reads the tuple out of the Redis list. Put that into a mini batch. You can set the size of the mini batch within your topology. Then it gives that to a bolt. This is an interesting point of view because here you have a join between a bolt and an external source, which is some CRM data. So we enhance the tuple with the the data of the current tuple coming out from the turbo curbogen. But we also add the group ID this client belongs to, because we will need that later for the forecast for the forecast computation. So next, you give that aggregation into a Trident using the aggregator API of the Trident API. So you have some aggregates you get out of your tuples. You have sum, mean, average, group by day, and contract type. We decided to create another spot which reads data out of the Trident state. It's stored in a memory map state, which is not a persistent storage, but it doesn't matter here. Then we give that to another Trident, which again does some kind of join with an external source with weather data. As you know, the electric consumption is very linked to the weather. Then the most interesting part here, you give that tuple to some adaptive model within R, and you wait for the result back. And you have the next day forecasting. You give that to, you store that in a Trident state. And on the top of it, we develop some gRPC function. We can plug a data visualization tool that can be used by an end user, and you can query the current data coming out of the smart meters, and you can have the current revenue, the revenue forecasting, but also the next day electricity consumption, which was the use case we wanted to address here. So why we have to use R? As Marilus said, we wanted to use R because we have a bunch of statisticians in EDF, and we didn't want to write everything from scratch. It was kind of a challenge here because you have only one engine by node, but you have many threads to trying to access this R process. So you have to make sure they are not going to try to access them at the same time. So you need to reduce the many threads coming into one thread and give that to R. Also, they are developing new models every day, so we can load the new model on the fly, and it works straight away. You have the result back. It's kind of difficult to instantiate. It took some time for us to make Storm and R work well together. It's a lot of settings to do to instantiate some environment variable, but at the end we succeed. And as you know, R is slow, so this is the bottleneck of our architecture. So we run some performance metrics, some tests. So this is a box plot out of 10 runs. This is the number of tuples processed per minute. So this is done with some kind of gentle configuration. As you can see, the standard deviation is very compact. That means the system is behaving in a stable way. So here we were able to process 500,000 tuples in 1 minute. We ran a second load test with a more aggressive configuration, and there we were able to process 3 million tuples in a minute. As you can see, the standard deviation is still very compact, which means the system is still behaving in a stable way, which is a good thing. Last load test, so an even more aggressive configuration. So here we are able to process 12 million tuples per minute, which is really good. What I forgot to say at the beginning, the goal of this POC was to process 35 million tuples in less than 1 hour. And with this test, you can see we were able to process 35 million within 4 minutes, which is a big success. As you see, the system, the curve grows in a linear way. So after 2 minutes, we already process 20 million of tuples, which was a success for us. We could, and the system was underused, very low CPU utilization and memory utilization. So we could even go further. And if one day we want to have data coming out of the smart meters every 10 minutes or even less, the system will be able to handle it. So as I said, we were newbies. We didn't know much about Storm. We made some mistakes, of course, but we learned from our experience. If we had to do it again, and if one day it goes into production, and I'm sure it will, we will change some stuff in here. So we noticed Redis, the buffer we used, could be a potential bottleneck if you have many tuples coming out from the smart meters and going into Redis. So we will go for a replication paradigm using the Redis master-slave, not topology, but architecture. Also, we will not use the memory map state, the Trident state. We will use HBase instead because it's a persistent storage, and it's already there in the Hadoop stack, the HDP stack. So, and it works well with time series. So why not using that? And also, since it's a persistent storage, if we have some failure, we can go back and run the topology where it failed because we know which was the last tuple processed. Also, rather than using a DRPC function on top of the topology, we'll directly query HBase, and HBase has got a high concurrency, so it will be the good tool if we had many end users trying to access it. So as a conclusion, I will say we had fun. Storm is a very great tool. We were very used to do some batch processing with HDFS, Hive, all the components in the stack. But doing some real-time computation, it's really enjoyable. It adds more values to the data. But this was a POC, so we did not have the production constraints. But if we had to answer some IT guy who wants to put that in production, we will have to answer some questions first. What about the resource sharing within the Hadoop ecosystem? But apparently, Storm on Yarn is on the way, so it could answer this question. What about the security as well? We are dealing with sensitive data here. We need to control access, maybe to encrypt the data as they are moving from one node to another. Also, Kerberos apparently is going to take care of it, so we need to wait for it and test it. What about the reliability as well? We didn't test it here, but if the Nimbus fails, what happens? How do you start over? These are the kind of question we need to answer. Alice, back to you.
And finally, this was a POC on time series, but Storm is used in operational conditions within our company in another context because it is used for supervising the communication network that comes with our meters. Some of the meters are deployed yet, so there is a communication network, and it is going to grow. So Storm is used for that. It has to process 8 million of events every day, and the objective of using Storm is to build KPIs on the fly for dashboards, for ensuring that the communication network is working well, for ensuring a quality of service. So they use a Trident, and Storm is used within a complex architecture with other components and with HBase and Kafka also for the events. Finally, here you can see different references of our work. So you will find them on the net, I think. And well, that's all. We are finished. Yes. We wanted to thank other people that were not mentioned in the first page and that worked with us. That's it. If you have questions.
Yeah. Yes, sir.
Can you tell us something about how you use space to training your R algorithm to do the forecasting? Because it is a slow part, right?
Yeah, let me go back to the... So, yeah, this is the slope part. This is the bottleneck of our architecture because R is very slow. It's like this. You have to deal with it. So what we do here to make sure it's not a bottleneck, we get data out of the Trident state, the aggregate, every 20 seconds.
Okay.
So which means you call R every 20 seconds and not in an incremental way on each tuple. You wait for some tuples to do some calculation, to queue, and then you process them.
But it's not really an issue because we have time to forecast.
Yeah, since it's calling an adaptive model, it doesn't matter if you call for one tuple of 1,000 of tuples, you get a reliable result back from R.
Mm.
Yeah, sure. Yeah, so.
Do you have some retraining schedule for the R algorithm? Basically used for, let's say, used for 1 month or 1 year, and then you need retraining the model, right?
Not sure about.
In fact, well, we're not a specialist of this algorithm, but the idea is that normally these models, these car models, are trained on big historical data, several years of data. We don't make a forecast, individual forecast. We make forecasts at aggregated level. So you have this model, and then the model, some parameters of the models are updated using the last data, maybe the last day of the data with the current weather forecast, etc. So every day the weather is retrained, not retrained, but some parameters are adapted.
Okay.
There is a reference, there is a paper in NIPS conference in 2 years ago, I guess, on the adaptive models. It's Yannick Good who is in EDF, the person that works on that subject.
Yeah, sure. Yes.
Just one
okay.
quick. The tuple that you have with 40 different values, does that represent 40 different attributes, or was that 30-minute samples or several samples of a single attribute?
Oh yeah, I went fast at this. So this is a one-day consumption for one client. It's 48 because you get electricity data every 30 minutes.
We decided to generate day by day.
Yeah.
Yeah, it's just.
Yep.
So for this particular use case, you really need to use Storm, or you just want to check the capability of Storm?
Yeah, we wanted to check the capability of Storm. But yeah, it's a real-time processing, but it's not. I mean, on the daily basis, it's on the daily basis, but it's not all day long. We have to process them within a window of time. So.
Here you waited for a day, right? You got 48
Yep.
meetings, and then you do it. So you might as well do a batch job. But I guess if you want to do it like within minutes, you could do it in Storm.
Yeah, we wanted to go fast, and we wanted also to. We don't need to wait for all the tuples to be processed to have what's going to be tomorrow consumption, electricity consumption. It's getting better and better as you dealing with more tuples, but you can have a result straight away as the topology goes on.
we can have an issue of having a forecast updated within the day.
Oh, okay. Got it.
Bonjour. In the triad state,
Yep.
there, which you want to replace with HBase, how much data you're planning to store there? Is it a historical storage right there, or is it just 30 day or 1 day, or and how much do you pipe through your R?
I don't really know. We can still it's in Hadoop cluster with a lot of disk space. I'm not sure what to answer. It could be. We don't really care right now, and it could be huge. Yeah.
For the R, we need to have the last day for updating. But I don't know if it's the questions. For the R, updating.
Just for R, but we could keep the result into HBase.
Yeah.
It wouldn't really matter. Yes.
One of the goals of the POC you mentioned was to compare your STOM with SEUPCC.
With other CP tool?
Yeah,
Uh,
right?
It's a sensitive question.
So what was the tool you compared and what was the result you got?
We didn't make a benchmark. It was not a benchmark. We wanted to see how Storm was working. So, for example, Streambase, we used Streambase for several years, and it has a development studio. So, develop applications with Streambase is more easy. Is easier than in Storm. After, Storm is interesting because it's integrated within Hadoop, and because also it is distributed. So we have a distributed architecture for our meters. So, well, we could see the objective was to see in terms of functionalities we could implement and we could implement. So.
If you had to reference right now, which one would you go with?
Sorry?
If you have to choose.
I don't have to choose for the moment.
But we have Storm. It's already there because we have HDP 2.1 cluster, so we have Storm anyway. It's there.
In fact, it depends. It depends on lots of things. If for operational with operational constraints, as Charles mentioned, security, support, etc., etc. So and of course money. So. But the tools are different. Streambase can be used for some applications, Storm for others.
So what's the role of that the Redis cache?
The role, it acts as a buffer. So because TurboCourbeGen emits data as fast as it can, so you need some kind of buffer because otherwise. If you plug directly TurboCourbeGen, you could plug directly TurboCourbeGen to the first spot, but as if the spot doesn't read fast enough, they put that in a memory, in a JVM memory, and it could crash.
You could use Kafka, right?
Kafka, yeah, Kestrel, any messaging. Yeah. We use Redis because it's there, it's easy to use. And it does the job well.
So the second question is, what's the latency for, I mean, essentially when you see the data until you can make a decision, what's the overall latency?
The latency of the topology?
Of the pipeline, yeah, essentially the whole pipeline. So by the time you essentially see the data for time t till the time you actually make a decision, how long does it take?
I'm not sure to answer right, but this is the latency. I mean, no, I'm not sure to understand.
I mean, throughput is just like how many tuples you can process, but you can process the tuple from yesterday. I mean, latency is just when you see a tuple, how long does it like pass through your system?
Yeah, but
we
as
use
it
guns.
is simulated data, the data is coming just right, and we process it. We didn't have really these questions. Well.
The answer to your question could probably be extrapolated given the number of batches, the size of the batch, and the throughput. But usually,
Go ahead, go ahead.
but they're using Trident, which is microbatch. So with that, you're more focused on throughput than you are capturing about 8 to 10 years.
I mean, you could potentially the batch just later back to back. I mean, you process a lot of batches, but you just process the data really late.
Thank you. Another question, yeah.
Since Storm has many configuration parameters, could you talk about the methodology that you followed in deciding the best values?
Sorry, I'm hearing one word over two, so can you speak a bit louder?
So I was saying, since Storm has many configuration parameters,
Yeah.
could you talk about the methodology you followed in deciding the values for these parameters to gain the maximum benefit out of the Storm?
We didn't use any methodology, actually. We were trying one set of configuration and then another, and using Ambari and Nagios and Goglia, you can see how the whole system reacts. So we are just trying, and actually, when we reach our goal, I mean, we did even better because we wanted to process 35 million tuples in 1 hour. Here, we were able to process them in 4 minutes. So for us, it was enough, but we could even push the system into its limit. But we didn't follow any particular methodology. It was just test, try, and see what the result is.
How are you planning to ingest data when you deploy in a live system?
You mean when it will go in production? When it's, I cannot really answer that.
No, I cannot neither.
It's too soon.
Yeah.
It's too soon.
It's too early.
Sorry.
Too early.
I'm not going to make this decision, so.
Yes.
Okay, any more questions? No? Thank you very much.